Hello everyone, my name is Barani, software engineer, and today I'm going to talk about the evolution and future of AI with a subtitle, or as I would like to call it, why large language models are amazing, but still not the end game, so to say. AI has come a very long way from handwritten rules to statistical models to deep learning to LLMs that can write poetry, debug code, and occasionally hallucinate with complete confidence, right? My intention today is to walk you through this journey, show what each era contributed, and try and explain why the story definitely is not finished. Why am I doing this? Because I wanted to clearly understand the progress of AI research and how we came about here in the first place. As they say, the best way to learn a subject is to teach it or explain it. Hopefully, this presentation will be of some use to you. By the end, I hope you'll understand why LLMs are powerful, why they are not AGI, artificial general intelligence, or human level intelligence, and why the future of AI is even more interesting than the hype or the burst of the AI bubble. So let's begin our story. Let's start with a formal definition. But instead of me reading it, I will ask AI to enlighten us. Let's see. Uh, Please define.
AI is a branch of computer science dealing with the simulation of intelligent behavior in computers.
Mhm. I'm not sure if you heard that clearly, but yeah, I outsourced the first line of my presentation to an AI. It's good to let the subject speak for itself, right? So AI actually has a surprisingly long history. So I asked Gemini to condense 80 years of research into 5 seconds because that's the attention span of all of us these days anyway, right? I'm kidding. So in just 80 years, we went from simple rules to learning machines to deep learning to the thing that now writes half your email replies. It was an incredible journey, but we are still missing something big. Now, here's the entire history of AI, but this time in a single image. And if your first reaction is, what on earth am I looking at? Perfect. I've been wondering that myself. This shows one thing very clearly. As training compute went up, AI went from recognizing digits to beating Go champions to writing your emails to correcting your code at 2 a.m. Each uh, each circle here in this chart represents one AI system. The circle's position on the horizontal axis indicates when the AI system was built, and its position on the vertical axis shows the amount of computation used to train the particular AI system. Training computation is measured in floating point operations here, or FLOP for short. A FLOP is a hardware agnostic metric for a single arithmetic calculation, equivalent to one addition, subtraction, multiplication, or division of two decimal numbers. Um, so if you see Thesis, built in 1950, was the first robotic mouse, and it was trained on around 40 floating point operations. And we can go so on and so forth. Then GPT-3 was trained on 314 million petaflops, and then till Palm, Minerva, they are trained on 2.7 billion petaflops. Um, but let's pause for a minute. We just saw how AI grew more powerful with more data and more compute. But here's the deeper question. What does it actually take for a machine to understand the world? Not just autocomplete text, not just play Go or chess, but actually understand. Let's meet our AI home assistant. This character will guide us through the evolution of AI. This robot is our test bed. It lives in a messy home, arguably the most complicated environment humans learn to navigate, at least babies. Each era of AI will try and often fail to help this robot function like a human. Um, a house is a chaotic environment. Lightning changes, objects move, residents create entropy. So a home has partial observability, dynamic objects, and the long horizon tasks. The different era of AI will all break in different ways, and this will hopefully highlight the limits of each AI better. We are about to see how each era emerged and where each failed or succeeded. We will start with symbolic AI. We will look at machine learning, deep learning, LLMs, agents, agentic AI, and world models. So, beginning with symbolic AI, what is symbolic AI? So, tracing back to the very beginning, uh, the era of rules and logic, symbolic AI was started around 1950s till 1990s. It was being used. Uh, so today we recall symbolic AI as a good old-fashioned AI. Everything was based on logic, if-then rules, for example, all propositional and predicate logic. There was no learning, knowledge was manually encoded, so the state spaces would blow up exponentially. We will see what I mean. Uh, let's understand, for example, if each object in the house has five properties and there are 10 objects, then possible states will be 5 raised to 10, which is 9,765,625 states. Impossible to write rules for, right? Symbolic AI assumes intelligence is rules, but real life has too many states for rules to cover. So, if our robot was rule-based, and let's say if we write rules like if red and cloth is sock, if round and red is tomato, a red round cloth breaks both rules. So, symbolic AI fails because it cannot generalize. Every new exception requires a new rule, and homes create infinite exceptions. So this is the combinatorial explosion that we talked about. So the we cannot write rules for every exception. It cannot scale. The weaknesses of symbolic AI, fragility, formal logic doesn't tolerate ambiguity or uncertainty. Brittleness, small environmental changes instantly break rule chains. No concept of similarity. A sock and a sock with a shadow are completely different states. Fails in messy real homes. So symbolic AI works only in perfectly defined worlds. Homes are not one of them. No learning, no adaptability, no continuous perception. So now we will move to the next era in AI. This was machine learning. Um, Machine learning was learning patterns from data. So this was dominant between 1990s to 2010s. Uh, Machine learning was the first major shift from rules to experience. Instead of programming knowledge, we let data speak. We'll focus on why machine learning was invented, how it mathematically differs from symbolic AI, why it still is not enough. In the machine learning era, the big shift was this. Instead of giving the robot rules, we give it data and it learns a function. At its core, Machine learning is simply function approximation. We want a model that takes some input x and produces some input y. So it learns a function f of x approximates to y. Think of it like this. In classical machine learning, the robot sees an image and the model outputs a label, socks, cat, cup, stain. So the whole goal was to make f of x match the correct label y as closely as possible. In short, machine learning is basically give me X and I'll predict Y. So if our robot was trained on machine learning, it would take an input image, you know, um, and it will classify the object in the image. So input is pixels and output is a label. Pixels of an image of a cat, and the output is a label that says it's a cat. A simple ML model to recognize an English letter, for example, would look like this. Let's say we want to recognize C, the English letter C. A weighted sum above a threshold given an array of pixels, uh, recognize the letter in the array. So let's say there is an array, 10 into 10 array of pixels representing a letter. Let's say this is the image. So the model computes um, W1x1 plus W2x2 up to WNxN plus B. And this gives the weighted sum. And it checks is the weighted sum greater than a given threshold. So the X's are the input features. For example, edge counts, curves. W's are the learned weights. These tell the model how important each feature is. B is the bias term, a baseline or a starting point, non-zero. And Y is the output prediction, the score. So the model here multiplies inputs by weights, adds them up, and checks whether the score crosses a boundary. Machine learning in this era was statistical pattern recognition, powerful, but still shallow compared to what comes later. So our machine learning based robot again will extract features like amount of red, texture smoothness, roundness. Then the model learns a boundary between sock versus tomato. This is the first time our robot can learn instead of being programmed, but only if humans hand engineer the features, color, texture, shape, edges. This is the classical machine learning pipeline. On the left, you see data collection, that is labeled data, examples with the right answer. Next, you see feature engineering. At this stage, humans manually design what matters, color, texture, shape, edges. Then the model learns a weighted function, for example, essentially adjusting sliders until it can correctly separate categories. Finally, you get a prediction, you evaluate and deploy. So how it would look like in our robot example. So it will start by collecting label data, thousands of images of socks, thousands of images of tomatoes. Human annotators do the labeling. It will extract features manually, edges. I mean, we have to handcraft the features manually, edges, color histograms, shape descriptors, and then the model will be trained against a classifier algorithm, SVM, support vector machine, logistic regression, decision trees, and then the predictions will be evaluated and deployed. The model will only work if test data is similar. So, for example, if lightning changes, shadowy room, red intensity drops, ML classifier mislabels sock as tomato. So this shows learning lacks robust perception. So, machine learning learns patterns, but only patterns we explicitly tell it how to see. So, it has robustness limits. Why machine learning will break? You'll see feature engineering bottlenecks. Humans must choose what matters. No hierarchy of features, no understanding of edges, shapes, objects, high dimensional brittleness, small pixel noise can move data across boundaries, right? One task per model. A sock classifier cannot classify a cup without retraining. So every for every task we need to train a separate model, you know. So that's impractical. Um, so machine learning learns patterns, but it doesn't learn representations. And representation is the real key to intelligence. So yeah, ML learns shallow patterns, not deep concepts. It only works with clean data. It fails in messy real environments. So now we move to the next era, deep learning. This is where things start getting exciting. Uh, with deep learning, our robot gets perception. Um, this era solves the ML bottleneck. No more feature engineering. The model learns features itself. So deep learning was the first time we stopped telling the robot what to see and allowed it to discover its own visual vocabulary. As we saw before in the machine learning era, machines struggled with vision. Classical ML depended on handcrafted features. Humans had to manually engineer things like edge detectors, texture descriptors, color histograms. The breakthrough of deep learning, starting around 2012, was the convolutional neural network, or CNN. CNN's architectures, though existed in earlier forms in the 1990s, but they became a dominant force in deep learning. Convolutional neural networks allowed machines to learn their own features directly from data instead of relying on humans to design them. A CNN looks at an image through many small filters that sweep over the pixels. Each filter detects patterns automatically, things like edges, corners, textures, and the whole network gradually combines them into higher level concepts. So the magical part is that this learning is hierarchical. For example, in the first layers, given an image, the network learns very simple patterns, you know, edges, gradients, small blobs. As we go deeper, this combine into curves, corners, textures. We go still deeper, and the network builds parts of objects, wheels, eyes, handles, fabric patterns. And in the deepest layers, the network recognizes entire objects, a sock, a cup, a face, a chair. So deep learning essentially is multiple layers of computational networks between an input and an output and its output. Let me give you a simple intuition for the math behind a CNN layer. When a CNN looks at an image, each layer is basically doing something like this. Uh, Sigma of W times X plus B. And here's what that means in very plain English. W is the convolutional kernel. It's just a small grid of numbers like 3 into 3 or 5 into 5 filter. This filter is what the network learns. It's looking for a specific pattern, an edge, a curve, a texture, a fabric pattern, etc. And X is the image patch. X is the little section of the image underneath that filter as it slides over the pixels. Think of it as the robot taking a tiny peek at the picture. And W times X is the convolution. The star symbol means convolution, but it really just means multiply the filter with the image patch and add it up. A high value means the filter sees the pattern it's looking for. A low value means it doesn't. And B is the bias term. It is simply a baseline offset, like we talked before. It lets the network shift the activation up or down. Sigma is the activation function, usually ReLU. It adds nonlinearity. This is crucial. It acts like a switch. If the pattern is strong, it fires. If the pattern is weak, it shuts off. This is what lets CNNs stack multiple layers without collapsing into a linear model. So each CNN layer scans the image, detects a pattern, fires a response if the pattern is present. And when you stack many of these layers, the network builds up more and more abstract representations, from edges to curves to textures to shapes to whole objects. So this is how our robot goes from raw pixels to actually understanding that something is a sock, for example, not just a red blob on the floor. So using CNN, our deep learning robot gets its digital visual cortex, just like humans. So for a sock, the layer one detects curves of fabric. Layer 2 identifies cloth texture. Layer 3 combines them into a sock outline. And layer 4 recognizes sockness, full reconstruction. All this achieved through backpropagation, an algorithm that sends error signals backward through the network and adjusts the weights. So the network didn't magically know how to recognize socks. It learned this through backpropagation, which adjusts millions of tiny filter weights to reduce error. All these filters, the ones detecting edges, textures, and shock shapes, are learned through backpropagation, backward error propagation across the network and adjusting weights so the robot gets better at recognizing socks each time it sees one. So CNNs in general build up abstractions just like our visual cortex. With CNN, we unlock new abilities. Our robot can now detect spills, recognize clutter, identify object boundaries, understand when an object is partially occluded. So the occlusion handling, CNNs learn to detect objects even when they are half hidden, rotated, or partly in shadow, invariances. Um, then our robot can differentiate between tomato versus red toy versus red sock now. So symbolic AI and machine learning struggled with these. Therefore, our robot now has stable perception, but still, perception isn't understanding. Now let's talk about reinforcement learning, which is how our robot learns correctness rather than just perception. The idea is very intuitive. The robot takes actions in the world responds with rewards for useful actions, penalties for harmful or inefficient actions. Over time, the robot learns which actions lead to good outcomes. So, in reinforcement learning, the robot learns what we call a policy, written as this equation, the probability of action A given state S under policy pi. This is just a fancy way of saying, given my current state S, what action A should I take? So if the robot is standing in the kitchen and sees a towel on the floor, the policy is the function that decides, should I move it left? Should I pick it up? Should I avoid the spill? Should I turn around? So we can express the robot's goal mathematically. Reinforcement learning tries to maximize the total future reward, which we call G, which equals the sum of gamma raised to t times r of t. Let me keep this very intuitive. Uh, r of t is the reward at time t. Gamma is the discount factor. The sum says, look ahead into the future, not just the present. Gamma controls the robot's personality. If gamma is close to one, the robot cares about the long term. It plans carefully. It avoids short-term shortcuts that cause long-term problems. If gamma is small, the robot becomes impulsive. It only cares about immediate reward, like a robot toddler. This helps us instantly understand what RL systems optimize for. It optimizes for correct behavior or correct action. Here are some simple examples of reward shaping for our home robot. So +1 for not bumping into furniture, +2 for picking up a towel correctly, -3 if it spills a cup, -5 if it knocks over a plant. Um, And over thousands of interactions like this, the robot begins to discover the safest navigation paths, the best way to grasp objects, when to turn, stop, or slow down, how to avoid frequent mistakes. So, reinforcement learning gives our robot behavior. Combined with deep learning for perception, reinforcement learning lets the robot actually act intelligently in the physical world. So reinforcement learning lets the robot improve through trial and error, just like animals. But reinforcement learning alone is too slow for real world intelligence. So deep learning has core limitations. CNNs can perceive, but they cannot predict what will happen next. They cannot understand physical causality. They cannot reason about goals. They cannot maintain long-term memory, cannot plan multi-step actions, cannot understand time, cannot simulate the world internally, cannot generalize. A CNN can tell you a cup exists, but not what happens if you push it. This is why we need LLMs, agents, world models, which we will see. So deep learning unlocked perception, but intelligence requires prediction and planning. Deep learning gives our robot eyes, but not a mind yet. Now we move on to generative AI, the revolutionary technology that we are using today. With generative AI, our robot learns language. So it exploded. It started in 2020, and we are still using generative AI. Um, So language is the interface between perception, reasoning, planning, and communication. LLMs predict text, not reality yet. Um, LLMs changed everything because language lets human compress knowledge. But predicting words is not the same as understanding the world. So why LLMs exploded? Four technical revolutions that made LLMs possible. Transformers, a new architecture that replaces recurrence with attention. Self-supervised learning. The model learns by predicting the next words. Given previous tokens, what is the probability of a next token that is is related to the previous tokens? Scale, more parameters plus more data gave new emergent abilities, which is nice. And the transfer of learning. One model can do many tasks. Now our robot can understand verbal commands, interpret writer checklists, ask clarifying questions, describe objects. LLMs gave our robot a brainstem for language, the first step towards general reasoning. So, everything you have heard about modern AI, GPT, Claude, Gemini, Grok, all of it rests on the single mechanism, self-attention. Basically, when you give a prompt to an LLM model, the LLM understands your prompt in this way. Each word learns to look at every other word in the sentence and decides who matters and by how much. For example, put the blue towel in the bathroom cabinet. So if you notice in the 5x5 attention heat map, blue attends to towel the most, bathroom attends to cabinet, put attends to in and cabinet. So how this works? This is the self-attention formula. It looks intimidating, but it's actually very intuitive. Here's what it means. In a sentence, each word becomes three vectors: a query Q, a key K, and a value V. Think of Q as what a word is looking for, K as what every word offers, and V as the meaning of each word. So we start by taking the query Q of a word and multiply it with the key K of every other word. This dot product gives us a similarity score. Basically, how related are these two words? A higher score means pay attention. A lower score would mean ignore. Now, we need to divide by square root of d of k to keep these scores stable, because queries and keys have many dimensions, sometimes 64, 128 or more. If you multiply two 128 dimensional vectors, the numbers get very large, right? Large numbers break softmax, the probability distribution. It becomes overly confident, and the model stops learning properly. To fix that, we divide the scores by square root of d of k. This rescales everything back to a stable range. It's basically a normalization step that prevents the math from exploding. Softmax turns these similarity scores into a clean set of probabilities, values that sum to one. This tells the model, here's how much attention you should pay to each word for every word in the sentence. Finally, we use those attention weights to blend the value vectors V, which contain the actual information of each word. This gives us a new vector, the updated meaning of the word we are processing. So the result, that is a meaning vector that says, here's what I should pay attention to the to in this sentence. So this entire formula is just compare, normalize, blend. That's the whole magic of attention. Self-attention measures how much each word should influence every other word. In short, the formula compares words, scales the numbers, picks the most relevant ones, and combines their meanings. Let's quickly visualize how that actually works. For a sentence, again, put the blue towel in the bathroom cabinet. Each input token embedding x1, x2, x3 up to xn, they are numerical representations of each token in the sentence after tokenization, embedding, and positional encoding. It is projected into three different spaces. Keys, what each word offers, its identity. Queries, what each word is seeking, what it wants to know. And values, the actual content that will be mixed to create meaning. So if the sentence is put the blue towel in the bathroom cabinet, the word blue has a query that asks, who should I modify? The word towel has a key that says, I'm an object that can be described. Here's the first important technical step. The, the query vector for a word is dot producted with every key vector. And dot product is simply a similarity measure. If Q2 and KI point in similar directions, then it means a high score. If they don't, then it is a low score. This is how the model decides how related are these two words. And then these scores go through a softmax function, which turns them into attention weights. Softmax probabilities distribution does two things: converts raw scores into probabilities, makes the most important words stand out. So the model learns pay a lot of attention to towel, some attention to blue, very little attention to bathroom when processing blue, and almost none to the cabinet. Finally, the attention weights are used to mix the value vectors. So the output is the attention weight times V. Each value vector uh, carries meaning. The weights tell the model how much meaning to take from each word. Uh, in a numerical example, imagine the attention weights for blue are compared to blue. The attention weights for towel is 0.72, cabinet 0.05, bathroom 0.03, put 0.15, in 0.05. That means the model says I'm mostly modifying towel, not cabinet, not bathroom. This mechanism lets the model understand who modifies who, what action applies to what object, which nouns belong to which adjectives, how phrases fit together, long-range dependencies. This is the core innovation that makes modern LLMs possible. Overall, if I have to say, self-attention is just a fancy way of saying find relevant relationships. It's very powerful, but it still operates only on text tokens. Now our robot begins to understand the language. So we looked at and tried to understand how an LLM understands the input prompt. Now let's look at how it generates the response. So this equation means what is the probability of the next token given everything so far, that is the prompt plus any generated output by the LLM model. That's the core of autoregressive generation. Uh, these are all the tokens the model has already seen. Our original prompt plus anything it has generated so far, they go into the transformer as a sequence. At every step, the model only knows the past, not the future. So the transformer uses its layers full of self-attention like we saw before to produce a representation of, given this history, what should the next token be? This is the internal thinking step. Um, the model then converts that internal prediction into a probability distribution over the entire vocabulary, about 50,000 possible tokens, for example. Each dot here represents one candidate token. Large circles means higher probability, small circles means lower probability. This is the model saying, is the next token likely the, for example, or robot, or a punctuation mark? The model chooses one token, sometimes based on the highest probability, sometimes it samples from the distribution, temperature, sometimes it applies constraints. That chosen token, xt, is the next token in the sequence. And then the magic happens. The chosen token is immediately appended to the sequence, and the entire process repeats. So the model goes understand, predict, choose, append, and repeat. This is the heart of how ChatGPT, Claude, Gemini, all LLMs generate text. So LLMs don't plan entire answers, they generate them one token at a time, constantly reevaluating the whole sequence as they go. Um, okay. Our home assistant robot, how it will be if it was trained on generative AI. So sometimes the robot would hallucinate. You ask, where did you put the towel yesterday? LLM answers in the cabinet. But the robot didn't do that. It's just generating a plausible sentence. Therefore, LLMs don't know truth, they know likelihood. Key limitations of LLMs: no grounding. They don't connect words to physical reality. A towel is just a word, not an object with mass, texture, affordances. No world model. LLMs cannot predict what will happen in the world. If the robot pushes a cup, if the robot turns left, if something falls. Zero physical reasoning. No persistent memory. Once context passes the window, it is forgotten. No causality. LLMs understand correlations, not causes. The cause and effect. No planning ability. Chain of thought helps, but is still token sequence simulation. Robot. If you ask the robot, is the towel wet? The LLM model inside it answers probabilistically, probably not. But the robot does not check the towel. This is the grounding gap. LLMs can guess, but intelligence requires knowing. Before we move on, we must acknowledge something important. LLMs were a big breakthrough we have never seen in the history of computing. For the first time ever, machines can interpret human language fluently. Machines can generate coherent multi-paragraph text. Machines can write code, debug, translate, summarize. Machines can learn from raw text without labels. Machines can generalize to tasks they were never explicitly trained for, zero shot and few shot learning. So this is not an incremental improvement. This is the largest leap in AI capability since the invention of deep learning itself. This revolution came from one key idea: self-attention plus large-scale training on the internet. But for all their incredible abilities, they also have very clear boundaries because they were never designed to understand the world the way humans do. Language does not equal physics, it does not equal planning, it does not equal intention. They can tell you what happens, but they cannot simulate what happens. They can describe a plan, but they cannot test the plan in their mind. They can talk about the world, but they do not experience the world, right? So that brings us to agentic AI, the next natural path towards making LLMs more useful outside just chatting. Agentic AI is about going from chatbots to autonomous actors. Uh, this is the beginning of LLMs being more than word predictors to behaving like planners, tool users, task executors, autonomous decision makers. Agentic AI is what turns a passive model into an active system. It's what turns an LLM into a system that can decide, act, observe, and improve. So, what is an agent? Uh, an agent is LLM plus memory plus tools plus environment loop. Um, so the loop is like this. sense input from environment, think an LLM model or a planner that's being used, plan, break into sub goals, act, take steps, use tools, call functions, observe, see results, and reflect, evaluate, or self correct. This loop is the core of AutoGPT, OpenAI's O1, DeepMind, Sima, Claude 3.5 agents, etc. So LLMs are not agents, but they become agents when connected to tools, memory, and feedback loops. So if our robot was an household CEO, and if we give it a task, clean the kitchen, an agent breaks this into sub goals, identify objects, grab a sponge, wipe a counter, load utensils in dishwasher, dispose of trash, inspect remaining dirt, verify completion. Each step may trigger perception, planning, tool use, memory recall, error handling. So this is not just generating text anymore. This is structured decision making. Why agents are a big deal today? Three key engineering concepts. Tool use. Agents can call APIs, run code, operate services. This allows automation across any domain. It can handle long horizon tasks, not just answering, but planning, executing, verifying, correcting. LLMs alone cannot do this, right? Reflection and self-correction based on system prompts or chain of thought. By the way, chain of thought is tricking the model into generating intermediate text that becomes part of the input. The model rereads its own words and uses that as external memory. It's autoregressive priming. So our agentic robot, uh, what does it do if wiping the counter fails? Its sensors detect water on the floor. Perception model classifies it as a spill. Agent updates environment state. LLM proposes next state, choose mop or avoid wet area. Agent recalculates new action, and the robot resumes the original task after the cleanup. Agents move LLMs from passive responders to autonomous problem solvers. Um, what are the limits of today's agents? Agents look impressive, but they have fragile mental models. Agents don't maintain a consistent world state. Their beliefs reset every loop. No real memory. They rely on short context windows, vector search, scratch pads. None of this is human like. Still grounded in text, agents don't understand objects, physics, or causality. Planning is token level simulation. Reasoning is generating likely next steps. Error propagation, bad observations, bad reflections, catastrophic loops. In our robot example, robot tries to open dishwasher, clean dishes, close dishwasher. If the robot misreads one observation, it may think dishes are clean when they are not, or think dishwasher is closed when they are open, and it will repeat steps infinitely. This is why agents fail in physical reality. Agents feel powerful, but they are still built on the foundation of LLM limitations. Agentic AI gives our robot behavior, but still not true understanding. Behavior does not equal reasoning, it does not equal prediction, it does not equal intelligence yet. So let's make an interesting calculation. Uh, an LLM is uh, a, a usual LLM model is trained on 2 times 10 raised to 13 tokens, 20 trillion. Each token, let's say, is 3 bytes. Then the total size of the tokens is 6 times 10 raised to 13 bytes, which is 60 trillion bytes. It would take roughly few thousand years for a human to read. If we 12 if we consider 12 hours a day, 250 words a minute. If we contrast that to a human child, in its 16,000 wake hours in the first 4 years, it's about 30 minutes of YouTube uploads. Um, it has 2 million, a baby has 2 million optical nerve fibers approximately, carrying about 1 bytes per second each. 1 million optical nerve fibers in one eye and 1 million in the other eye. Then the size of uh, the information the baby learns is 10 raised to 14 bytes in 4 years. So a 4-year-old baby has seen more data than an LLM. So this is the limitation of LLM, right? So what next? Where do we go from here? Everything we have seen so far, LLMs, agents, tool use is incredibly powerful, and it's happening today. But these systems still lack something fundamental. They do not understand the world. They can reason in language, but they cannot reason in reality. And that's where the frontier begins. The next decade of AI won't be about predicting the next word. It will be probably about predicting the next state of the world. So, predictive world models. Every major AI researcher today tends to agree on one thing. LLMs, as powerful as they are not enough to reach real autonomy. They give us language understanding, coding ability, abstractions, even creativity, but they do not yet have a model of the physical world. And to build truly intelligent systems, robot agents, assistants that can act reliably, we need something deeper. That deeper layer is called a world model. No one has articulated this direction more clearly than Yann LeCun and the FAIR research team. Yann LeCun, I've been following the work of Yann LeCun, and he's regarded as one of the three godfathers of AI. But not because we are choosing one researcher to follow, but because this architecture fills every gap that LLMs leave open: grounding, perception, prediction, causality, planning, consistency. This section that we are going to see is not speculation. These models exist today. JEPA, latent object predictors, video world models, Sora, for example, it's getting there. Most of these systems are working in labs right now. They are the foundation of the next generation of AI, I believe. We shift from predicting words to predicting the world. This is the difference between ChatGPT-like intelligence and animal-like intelligence. So if LLMs can understand language, world models uh, attempts to understand reality. So why we need world models? Our robot must be able to predict the future, right? It has to know the consequences. If I push this cup, it falls, it spills, the liquid spreads. It has to understand the object permanence. If the towel is behind the microwave, it's still there, and it's going to be there. LLMs can do this. They only predict words. A world model learns a transition function. It predicts the next state of the world given the current one. So ST is the current latent state of the world. Latent state meaning a latent vector representation that captures the essential structure or meaning of the input while removing unnecessary details. It's like the hidden abstract representation the model uses internally, a compressed form of the essential information. A picture of a cat becomes a latent vector. A picture of a cup becomes a different latent vector. So ST plus 1 is the predicted next state. This is the core of intelligence, anticipating what happens next. Our home robot cannot operate safely unless it can predict, if I move this, what happens next. Babies learn this at just 6 months. The deep idea is simple. Intelligence is the ability to predict the consequences of actions. World models make this possible by learning a function that maps the current world into its likely next state. So why not just predict pixels? Um, Predicting pixels is impossible and unnecessary, right? So a 1080 pixel frame has about 2 million pixels, and the next pixel prediction is astronomically hard. Tiny errors break everything. Humans don't predict photons, we predict abstract states. Instead of predicting raw pixels, world models predict latent states representing object positions, velocities, affordances, relationships, physical dynamics. We don't look at a cup and predict every pixel of the next frame. We predict the cup will fall, liquid will spread, I must adjust grip. This is why world models operate in latent space. They predict what matters, not what everything looks like. This idea prepares us for JEPA. But before understanding JEPA, we need a tiny bit of historical context. One of the oldest and still most elegant ideas in machine learning is the energy-based model, or EBM. An energy-based model doesn't predict labels or tokens. Instead, it assigns an energy score to configurations of variables. Good, consistent configurations have low energy. Bad or impossible configurations have high energy. Think of it like a landscape. Correct interpretations of the world sit in valleys, and incorrect ones sit on hilltops. This is the conceptual ancestor of many modern AI models. Yann LeCun has been one of the central pioneers of energy-based models since the 1990s. His work on energy functions, contrastive learning, sparse autoencoders laid the groundwork for models that learn good representations without requiring labels. The core idea behind energy-based models is don't predict a specific output, learn a scoring function over representations. In other words, not what is the next pixel, but is this representation consistent with the world? This is the philosophical bridge. JEPA, the joint embedding predictive architecture, which we will see next, is a modern evolution of this idea. Instead of predicting pixels or tokens, JEPA predicts future latent representations and evaluates how consistent they are. So, in short, EBMs learned what configurations make sense. JEPA learns what future configurations will make sense. This is why JEPA avoids pixel prediction entirely. It focuses on meaningful latent space. So why energy-based models matter? This is important because predicting raw data like pixels or tokens is incredibly wasteful and often meaningless. What we want to predict is the state of the world in an abstract latent space. EBMs pioneered this separation between raw input and internal representation. JEPA takes that idea and turns it into a modern, powerful predictive machine for the future. So, JEPA, Joint Embedding Predictive Architecture. JEPA is part of the recent wave of architectures proposed by LeCun and the FAIR research team, as I told. You can think of it as the descendant of the energy-based models that shaped a lot of earlier representational learning research. So in a sense, JEPA is the modern scalable predictive successor to energy-based models. Instead of modeling what is, it models what will be. So JEPA, a predictive model that avoids token prediction entirely. Here's how it works. Let's say our robot sees the current world state, then it encodes it into a latent vector. Then a predictor model forecasts the next latent state, and the next real frame is encoded. And the training using loss function happens, which simply reduces the distance between the predictive latent and the actual latent. Why is this powerful? Because JEPA learns world dynamics, how things move, fall, collide, interact. This is the foundation of real physical understanding. Um, why JEPA is close to AGI compared to LLMs? Because LLMs cannot predict next tokens, right? We already talked about there's no notion of truth, no world consistency, no physics, no causality, brittle extrapolation. JEPA predicts next state, learns causality, learns invariances, learns object dynamics, grounded in physical reality, consistent world model. So if an object is hidden, if it's rotated, it doesn't matter. Uh, World models will still recognize that object. So LLMs are brilliant linguistic machines. World models are the missing cognitive layer. Our robot with a world model can predict the cup will spill, the floor will become slippery, the vacuum battery is about to die, that cleaning the floor now creates a hazard later. Our robot can plan, reorder tasks, navigate safely, avoid hazards, optimize goal achievement. This robot now has something LLMs lack, a simulation engine in its head, just like humans. With the world model, the robot stops reacting and starts anticipating. So, what is autonomy? Um, Autonomy is perception plus prediction plus planning. LLMs solve perception plus language. World models solve prediction. LLMs are necessary but not sufficient. LLMs were a huge leap forward, but they are missing key ingredients of intelligence. Let's be precise. What they are missing? Like they are professional guessers, not world modelers. LLMs have context window, short-term scratchpad, no built-in long-term memory, no stable self-model, no evolving knowledge base apart from fine-tuning or if you provide the data. When context expires, past is gone. So in our robot example, if it saw the towel on the chair earlier, but that's no longer in context, it has no structured way to remember. You have to bolt on vector DBs and memory stores manually. Humans don't forget their own life story when a conversation ends, right? Humans learn language from very few examples, physics just by moving around as babies, social dynamics through observation. But LLMs require trillions of tokens, enormous compute, offline static training. So an AGI that needs the entire internet every time it learns is not feasible. We need self-supervised, continual, grounded learning, not just text pre-training. Just scaling alone won't fix this. Um, Even if you 10x the parameters, 10x the data size, 10x the compute, LLMs will still hallucinate, lack grounding, lack stable memory, lack stateful world models, lack long-term planning. It will still confabulate answers. Scaling doesn't change the objective or the architecture, the underlying architecture. You don't get a world model by making your autocomplete bigger. So what we actually need is we need systems that learn representations of the world, JEPA style, predict future states, world models, optimize a cost function, goals, rewards, constraints, use an actor module, policy that chooses actions, learn primarily via self-supervised interaction with the world. LLMs can be part of this stack, but they are one module, not the whole brain. They are an amazing interface to intelligence, but not the engine of intelligence itself. So the engine is world models plus planning plus self-supervised learning. LLMs will plug into that engine as a powerful language interface. Now I'm almost at the end of my presentation. The staircase of intelligence, coming back a full circle, we will put it all together. Uh, with symbolic AI, the knowledge was hand-coded rules, logic systems, machine learning, pattern perception, deep learning, robust perception. It was using CNNs, hierarchical features, LLMs, language understanding, semantic reasoning, emergent abilities, agentic AI. So it was about action, planning, tool use, reflection loops, world models, understanding, causality, prediction, physical reasoning. Every step in AI history solved the bottleneck of the previous step, but only the combination brings us close to human-like intelligence. So, how our robot finally becomes intelligent, to say it has memory for continuity. It should have LLMs for language. It should have cost functions for goals. It should have CNNs, vision models for perception. It should have agents for behavior and world models for prediction. We began with the robot in a messy house. Through the eras of AI, we gave it eyes, language, tools, actions, but it only becomes intelligent when it can predict. So, what this means for engineers, I believe AI won't replace engineers, but engineers who understand AI will replace those who don't. Those who master LLMs will build the interfaces. Those who master agents will automate workflows. Those who master world models will shape the future. Those who master AI safety will lead regulated industries. Those who understand all these pieces will architect intelligent systems. I believe the real opportunity is not using AI, it's shaping the systems that define the next decade. Thanks for listening. I hope this presentation gave you enough architectural perspective to understand AI around us and how they evolved. Uh, have a nice day. Um, Bye.